So when I asked if what we could contribute here, I was asked to present our work on LiFi for Industry 4.0, which is one of the use cases that we have been looking at quite intensively. So basically, I will give a short introduction, then I will more go into the concepts for industry, which are important. So this is, and then I will hand over to Leonard. He will speak about the 15.13 standard he has been working on a lot. So I think you have seen this slide in various versions today. So LiFi is mobile communication by using the light. So we want to really enforce this mobility as a new feature of light and communication. So it's mobile, bidirectional, high-speed data. We need no RF. We have been asked what are the unique selling point of this technology, and I think one of the most important ones is you can build these ultra-dense deployments. So when you compare this to Wi-Fi 6, we are in the order of 1 megabits per second per square meter. When we look at this LiFi first generation, we start at around 100 megabit per square meter. That is really a big jump that is possible by this technology. Then we can leverage a few other things, that it does not go through walls. There's no interference with radio, and the spectrum is unregulated. So we in Fraunhofer, we have built a number of prototypes, and I think our specialty is that we can tailor those prototypes to different use cases, and we have studied quite a lot. So industry, hospitals, residential, also in outdoor environments. I'm just talking about the industry use case today. So we had a project together with the company BMW several years ago already, and when we came in contact with the company, they said, go away with the gigabits. We don't need them. What we need is something else. If you can replace this, so maybe it's, if you can replace this button, which is very has to be very secure. If you can replace this, the connectivity of this link with a wireless link, then we would buy your technology. So that is robustness and security are one of the major concerns that those industry people had. So they had concerns that their production line could be jammed from the outside. So that would stop the production. They produce 1 car per minute, and you know what these cars cost. So the damage that would be caused by an interruption of the wireless service in industry would be enormous. And so they want to have absolutely reliable communication. So privacy, no jamming. Robustness, no packet loss is one important thing. There's something that is under discussion right now in the framework of resilience. So some sort of self-healing capabilities that could be addressed by operating multiple air interfaces in parallel. And the robustness against electromagnetic interference is a very big argument also for industry, in case you have some sort of work ongoing there that creates electromagnetic interference that would disturb the wireless link. Mobility, it's kind of a gradual requirements, as they ask for mobility, high mobility just inside one manufacturing cell. There should be no interruption due to the when you block the line of sight. But when you go outside of the manufacturing cell into another hall, also there should be some sort of nomadic or high-speed mobility if you go to other facilities. There is a debate what kind of latency and jitter is required. And so the normal factory automation requires 1 to 100 milliseconds and 15% jitter. But if it comes to motion control, it's in the order of milliseconds and 1%. So for the demanding control applications, jitter is a serious issue. So what can LiFi do for the Industry 4.0 is it is secure. It has been said many times that you can confine the light in a room. It's robust against jamming and the electromagnetic interference, and it is direct. That means it travels by the line of sight, and that is a big advantage in terms of doing time synchronization. There is no, your beam does not go to the next room and bouncing back. So, and that also helps a lot in terms of positioning. I will come to that point. LiFi is robust. Of course, our biggest problem in this deployment here was that the line of sight can be blocked. And we have solved this by using more than one link. So if one link is blocked, then there will be another link that can take over. And we just have to combine them in some way. And that technology is called MIMO. And when we introduce MIMO into LiFi, then we can overcome the blockage issue. And it has to be mobile, so we have to look into a handover to Wi-Fi. Basically, if we go from one room to the next, and to 5G if we go to outdoors, of course. So why do we need low power? So that was, people are always asking the same question. So we are really, so sorry, I'm going back. So when you deploy LiFi, I've even seen that on slides, on several slides today. Very narrow cones, just very small overlap here. What happens if you have the link here? If there's a blockage, then this link will be broken. What you need for a reliable connectivity is a connection to that other access point here. And therefore you need much wider cones. So actually we have to ensure that those beams are overlapping substantially in order to have connectivity even in case some of the links is blocked. So this overlap is important, but it will lead to an reduced intensity here in this beam, and that means our link budget is used up by the need for reliability. So what we can do here is we can have a look into new modulation schemes that don't use OFDM but use something else like on-off keying that is much more power efficient. And what we have seen, it's very important to combine that together with a technique called frequency domain equalization. It sounds like something entirely new, but it is really simple. It's basically, if you look into this is an old paper from David Falconer. He is a professor in Canada. And when you look at an OFDM system, there's an IFFT, and you take this IFFT out and move it to the end of the transmission chain, so from the transmitter to the receiver side, and you convert an OFDM system into an OOK FDE system. So basically then this is the frequency domain equalization, and it's just a shift of one module in the whole pipeline that has of course some further implications up in the protocol stack. Then the question was, how do we adapt to the data rate? In a mobile scenario, your capacity is going up and down when you walk through the room, and the on-off keying has just two levels. How do we do that? And the idea, which is quite straightforward, is you can adapt the baud rate here. So this factor B in front of the capacity formula of Shannon. So when you have a variable baud rate, you can adapt to the different signal quality you experience in a room. A second issue is how to overcome this blockage, and this is a technique we have called distributed MIMO. So when you look at the conventional handover that we have also seen today, the user is just covered by one access point. Yeah, and then when he comes to the next the coverage area of the next access point, he is disconnected and reconnects to the access point. So this is usually processed in the higher layers, and there can be hundreds of different ways of doing such a handover, but usually you have to take a period of time with errors into account, and it also causes latency of the packets that have to be delivered after the handover has taken place. So when we do distributed MIMO, that is different. The devices are then no longer covered by a single access point, but somehow we have this coordinator here that is connected to multiple optical front ends, and those maintain links in parallel to the devices. So there is a so-called fronthaul from the coordinator to the distributed optical front end, and then we can have, for instance, a dynamic selection of the front ends and even transmitting the same signal over two of them in parallel, so that there would not be any blockage in when we move from one cell to the other. This all is processed in the lower layer, so in the physical and the lower MAC layer, and it can be super fast. The idea is, of course, taken over from 5G. This is called a Cloud RAN, and this distributed MIMO makes the LiFi robust against blockage, and it allows low latency and 0 bit error rates. This is maybe a bit complicated concept. Leonard can better explain it than me. So when you have a distributed array of LiFi access points, then under normal circumstances, one of the users is covered by a cluster of these access points. And here there's another user, and because those two users are covered by two different subsets of the access points, they can transmit in parallel, and that is called special multiplexing. So we can double the capacity by transmitting in parallel over those links. It can happen that some of the users have overlapping clusters, and in those cases, we suggest just to split the time domain. So there is a channel estimation and feedback protocol that is needed for that, and that is also implemented in the 802.15.13 standard. I think that's also the differentiating thing, that we have this protocol implemented, and it's supported by the LiFi and the Mac. One great thing that has been investigated in the framework of the ILIOT and also in the Vision project was that the integrated positioning, that when you have this distributed MIMO architecture, you can do very nice 3D positioning. So we have no GPS indoors, but the general idea in wireless communications is to integrate that into the communications capability. And when you look in Wi-Fi, it's a very difficult. I can explain it in detail why there are problems with Wi-Fi to get good precision. It's basically due to the multipass and the penetration of the signal into the next room. The LiFi only travels through the line of sight if it's available, and so it really has a single very sharp peak if you from which you can measure distance. Our proposal was to integrate that directly into the communication protocol. So basically you do it in 2 steps. You first do a coarse timing by reusing the sync header in the physical layer preamble. And the second step is you do a fine timing that is based on the channel estimation and eventually some MIMO pilots that have to be added to the standard. So you can see here, so the blue curves is the coarse. The coarse one is of course not very precise. Then there is the fine timing, that is the red curve. And if you subtract the two from each other, you get, or you add the two, then you come to this yellow curve, and you can see it's very accurate. So you can do very accurate positioning by means of LiFi. It's really working on the centimeters level. Okay, then I would hand over to Leonard.
Thank you. So my name is Leonard Bober. I'm the technical editor of the IEEE 15.13 standard task group. Volker asked me to give a few minutes of an overview on that standard. So the task group actually split up from the existing 15.7 R1 group in, I think it was 2018 or 17. And we removed a lot of, it's quite a while ago, we removed a lot of the functionality that was in there. So there was a lot of legacy functionality that wasn't really reused. There was an optical camera communication in it. And we tried to really create a very simple standard. And amendments will allow in the future to add additional features. And also the goal was to realize really the unique selling points of LiFi, especially with regard to industrial communication. So taking all the things that Volker just said into account, we have a big picture of a LiFi network with distributed optical front ends in the ceiling. We have a front haul network that basically distributes the data towards those from a central switch or entry point, which is integrated into a local network. And we have devices that communicate on the factory floor with some applications like control in the local cloud. And the task group aims to create a simple standard for that. The main features to support here are that distributed MIMO that Volker talked about, the cell-free mobility without having a logical handover between access points, deterministic access for real-time transmission, and also compatibility with IEEE LANs. So starting with the physical layers, we have two of them. IEEE is always frame-based physical layers. So we're a certain PPDU structure, it's called, with a preamble header and stuff. And the first physical layer is called PMFi. It's based on off-keying, 8B, 10B, to get rid of the DC, and Reed-Solomon forward error correction. It's aiming at high reach and energy efficiency, as Volker said. And it supports that exact frequency domain block equalization. You can see the transmitter structure in the bottom, but let's focus on the HB-Phi because lack of time. So that is, Max told us before, it's derived from the ITU-T standard, G.HN. It's based on DCO OFDM with adaptive bit loading, LDPC FEC, and it's providing high throughput and up to 200 megahertz of bandwidth. So those two physical layers basically support the kind of opposite goals in order to realize, for example, the uplink with energy efficient physical layer and the downlink with an spectrally efficient physical layers. In the medium access control, we have a single coordinator as in the picture before and distributed optical front ends. And logically, we have a star topology. So there's really just the single coordinator to which the mobile device is connected. And the front haul connection connects all these. And the goal is to allow any front haul. This, however, has some implications because if the front haul, for example, is realized over a digital technology, you know that from radio networks you can have a certain latency. So certain things don't work anymore, like CSMA ACA, or for example, immediate acknowledgements or so. So all is focused on TDMA to allow also timely transmission over the front haul without being time critical. You can just schedule the transmission over the front haul. We have periodic CSI feedback loops specified that allow us to measure the channels between the member devices and the optical front ends in order to allow the coordinator to schedule which optical front ends to use and allow this cell-free mobility. And ultimately more features to support that front haul setup, like delayed acknowledgement, block acknowledgement, stuff like this. The network integration is important in order to seamlessly integrate LiFi networks into existing networks. We heard before that it's really important that LiFi isn't a replacement for RF, but it's a complement. So the goal was here to implement, to integrate LiFi networks with existing IEEE LANs. And the relevant standards are here, IEEE 802.1ac and 802.1q, which define the MAC service. So we tried to fulfill the interfaces that are really required by those, so we can integrate LiFi seamlessly. This also allows us to directly support some of the features that are defined by IEEE, for example, in the time-sensitive networking group. It's not yet developed, but it will be. This will make it easier in the future. For example, there's a standard for redundant transmission of packets in industrial networks over different paths. So we can, for example, transmit packets over radio and LiFi and just eliminate the duplicates, increasing reliability. Ultimately, we're prototyping that standard. The outlook is as follows. We'll finalize it this year. We're prototyping it. You can see a picture of a rack. It's not very tidy, but it's based on a cloud-based software for the coordinator, so that access point software runs in the cloud, basically on any server that has certain PCI Express cards. We're prototyping the FPGA, the physical layer on an FPGA, and have embedded protocol software stacks for the mobile units, for example, for the mobile devices. In the future, we hope to add additional features in amendments and try everything out in pilot installations. So we introduced, we had some demos for LiFi. First of all, we integrated LiFi with 5G. That is not really done with the 15.13 standard, but with our other devices based on the I2T chipset. The goal is here that we have the flexibility to integrate mobile devices over any mobile communication link. We have two reliable technologies, and technical challenges were to integrate it in the 5G core and to have a decision mechanism to decide what link to use, 5G or LiFi. Lastly, we had a demo on positioning. We had those two cells with 6 optical front ends and performed measurements and tracked the receiver. And you can see here in the graphs that we could reach in the real world experiment really a high precision of a few centimeters error only. What's coming now? So currently we're working on a project LinkNet to develop LiFi further for industry and medicine. We have one goal, that is to integrate Powerline and LiFi as well there in order to lower the threshold of market integration, market introduction. But also we're working on that prototype and distributed MIMO system to basically go to the next level of LiFi with this distributed MIMO front-haul system concept. In summary, LiFi has become increasingly mature in the recent years. Industry 4.0 requires many of the unique selling points that LiFi provides. And some of the new features are low power, distributed MIMO, integrated positioning, the handover between radio and LiFi. And with 15.13, we're trying to support these requirements and develop it. And we showed some working demos of LiFi in the project Elliot as well. Thank you for your attention.